students, we're going to do group 1 elements right now. Just write this down, group 1 elements. Now, when we talk about group 1 elements, it refers to the elements that have one valence electron, okay, meaning one electron in the last shell. So let's look at group 1. The elements we have are hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Okay. Now for this group, we don't refer normally to hydrogen. We only refer to the rest of them. Okay, because hydrogen is a gas, and because this group is called alkali metals. So don't worry about the hydrogen, focus on the rest. So group 1 is called alkali metals. Okay, they each have one valence electron. Let's talk about some of the properties of this. Since it's a metal, guys, group 1 metals are shiny. They are gray in color, and these things, they don't test this on the exam, but I'm just giving you some info. Okay, gray in color, they are shiny, and they have low densities. Does this really matter for SPM? Not really. You just need to know that they are alkali metals. Okay, so let's talk about some of their important physical properties and why those trends occur. So I'll just write down the elements: lithium, Li, sodium, potassium, rubidium, cesium, I can't remember the symbol, I'll just put down cesium, and francium. Now the ones that you really have to remember are the first 20. Lithium, sodium, and potassium fall in the first 20 elements. So don't worry about the rest. Remember lithium, sodium, and potassium. Okay, guys? Proton number. For lithium, I'll just write down Pn stands for proton number. Lithium is 3, sodium is 11, potassium is 19. Okay, we won't talk about the rest. Density, one of the important features, physical properties. Density of lithium, 0.53. Density of sodium, 0.97. Density of potassium, 1.02. So, guys, what do we see? Does the density increase or decrease down the group? Like group 18, the density increases as we go down the group. Okay, so I'm just going to write that down here. Density increases down the group. Okay, and why does this happen? The same reason as why the density increases in group 18, guys. So the density increases down the group because the change in atomic mass is greater than the change in atomic volume. Same thing as group 18. Okay, atomic radius. AR stands for atomic radius. So atomic radius for lithium is 0.15, for sodium is 0.19, and for potassium is 0.23. You don't have to worry about these values, you just understand the trend. Okay, so tell me about the trend, guys. Does the atomic radius increase or decrease? As we go down the group, the atomic radius increases, same as group 18. And why? It's the same reason. Think, what is the electronic configuration of lithium? 2.1. Electronic configuration of sodium? 2.8.1. Electronic configuration of potassium? 2.8.8.1. What is increasing? The number of shells. So that's why the atomic radius increases as we go down the group, because the number of shells filled with electrons, remember the keyword, filled with electrons, increases. Okay, guys, we good so far? Now, we talk about the melting and the boiling point. So this one is a little interesting. Okay, guys, it's not the same as group 18. For group 18, we said very low melting and boiling point, but in group 18, the melting and boiling point increases as you go down a group. What about for group 1? So I'll just write down the elements: lithium, sodium, and potassium. So melting and boiling points, I'll just write M and P. Melting point of lithium is 181, for sodium it's 98, and for potassium it's 64. Now guys, look at this. Isn't the melting point decreasing? This trend is a little different from group 18. In group 18, the melting point increased as we went down the group. And what was the reason? We said that because we have more shells filled with electrons, it's going to be harder to break those van der Waals bonds. Remember guys? But here, as we go down the group, the melting and boiling point decreases. Now, the reason for this, guys, believe it or not, is the same. It's the same reason actually, but this may not make some sense to you, but try to understand me, okay? As we go down the group, the number of shells filled with electrons increases. But in group 1, unlike group 18, the bonds are not van der Waals forces. The bonds are called metallic bonds, metallic bonding. Okay, these are the bonds between the atoms. So when you go down the group, the number of shells filled with electrons increases, and when that happens, the bonds become weaker. It's opposite to group 18 where the bonds become stronger. Why the difference? Because in group 1 you have metallic bonding, which works differently. In group 18 you have van der Waals forces, which works differently. So when you go down the group in group 1, melting and boiling point decreases because the number of shells filled with electrons increases. Therefore, metallic bond decreases, and so you need less heat to break the bonds. Does that make sense, guys? Awesome, awesome, guys. That was a big difference between group 1 and group 18. So please take special note of that. Now we are going to look at some more properties. Let's see. Another important thing, guys, is that group 1 metals are extremely reactive. Okay, when I say extremely reactive, I mean that they will catch fire. They're crazy. So in order to prevent them from reacting with oxygen, reacting with the air, like for example, if I take a piece of lithium, right, and expose it to the atmosphere, it may catch fire. It's that reactive. So what do we do about this, guys? There is a type of oil. It's called paraffin oil. Okay, remember this, paraffin oil. You need to always store your group 1 metals in paraffin oil. Okay, just put them in there and they will not react with oxygen in the air. They will not react with water. Everything will be safe. So in a SPM question, if they ask you, name some safety precautions for group 1 elements. So you think back, okay, group 1 is damn reactive. So how do we prevent it from reacting? We place it in paraffin oil. That's it, guys. Okay, you good so far? Let's continue. Okay, now moving on, we still talk about reactivity. Group 1 metals, as I mentioned, are very reactive. And what do I mean by this reactivity? Let's take the 3 elements again: lithium, sodium, potassium, and we talk about their electronic configuration: 2.1, 2.8.1, 2.8.8.1. Okay, so all these 3 elements have a valence electron of 1. So in order for them to be stable, they need to not gain 7 electrons but lose 1 electron. You get it, guys? So reactivity for group 1 elements is the ability to lose that 1 electron in the valence shell. Okay, and as we go down the group, reactivity increases. So I'm just going to read what the book says. For group 1 elements, the reactivity increases when you go down the group. We already mentioned this. Each atom of alkali metals will release one valence electron during chemical reaction to achieve a stable electronic arrangement of a noble gas. We said this as well, right guys? Losing one electron, becoming stable. Now, the reactivity of an alkali metal depends on its ease, or how easy it is to release the single valence electron. The easier it releases the single valence electron, the more reactive is the alkali metal. Okay guys, and as we go down group 1, the atomic size increases, right, because more shells filled with electrons. So think about this logically guys. Okay, let me draw out the shell for lithium. Okay, this is lithium 2.1. Reactivity is based on the valence electron. How far is this valence electron from the center of lithium atom, the nucleus? The nucleus is the center. How far is it? Not too far, right? There is there's an electronic attraction that goes place between this last electron and the nucleus. Okay, compare it to sodium 2.8.1. 2.8, 2, 3, 4, 5, 6, 7, 8, and the last shell 1. You see this guys? This valence electron of sodium is further away from the nucleus than the valence electron of lithium. Therefore, the pull of the nucleus towards this valence electron is more for lithium than it is for sodium. And obviously for potassium, it has 4 shells. The distance between the last electron, the valence electron, and the nucleus is going to be more, further apart. The greater the distance between this valence electron and the nucleus, the greater the ability to lose the electron. Think about it guys logically. Far away, easier to lose. The closer the electron is to the nucleus, the more it's going to stay, because the nucleus is pulling it closer. Alright guys, so reactivity increases as we go down the group. Do you get this guys so far? Awesome. Alright, just think logically, never be afraid of chemistry. Okay, so another property of group 1 metals is that alkali metals can burn in chlorine gas or sodium or bromine gas, sorry. So let's write down the equation when lithium reacts with chlorine gas. Lithium is a metal. This is a chemical equation, so please study chemical equations before doing this guys. Lithium is a metal, so it's by itself, Li, reacting with chlorine gas. Chlorine gas is Cl2. What product do we get? Now whenever we form the product, remember we have to use the chemical formula rule. Lithium is Li plus, chloride is Cl minus. So what do we get? 1 and 1, so we get LiCl. Can we balance the equation? 1 lithium here, 1 lithium here. 2 chlorines here, 1 chlorine here. Put a 2 here, now we have 2 chlorines, 2 lithiums. Put a 2 here, we have 2 lithiums. This is how we balance the equation. Alright guys, now we're going to look at the most important part of group 1 elements. There are 2 experiments, okay, we're going to go through them. So stay with me on this guys. There are some things we have to memorize, okay. So just give me a second guys. All right. So the first thing we're going to talk about right now is we are going to investigate the chemical properties of group 1 elements, okay? Primarily the reaction of group 1 elements with water. So don't worry, don't read about all this. We're going to I'm going to explain the experiment to you, okay? What we're going to use is lithium as an example. So you take a piece of lithium, you put it in water. That's all you do. Observe the change. Then at the end of the reaction, you take a piece of red litmus paper, put it in the solution, see what happens. That's it, guys. This is the experiment. So let's look at our observations, and you guys really need to know these observations, okay? This is so important. Please understand this. Lithium. What happens when lithium reacts with water? Lithium moves slowly on the water and it produces a hiss sound, okay? And the solution turns red litmus paper blue. Why does it turn red litmus paper blue? We'll come to that. So let's think about this, okay? So lithium, place it in water, it moves slowly, produces a hiss sound. Moving on. Sodium, same thing except that it moves faster in water, also produces a hiss sound, and the solution turns red litmus paper blue, same as lithium. Now for potassium, the last one, it's going to move way faster than lithium, way faster than sodium. It's also going to produce a hiss sound, but guess what? Not only that, it's going to produce a pop sound as well. This is the key word for potassium's reaction with water, pop sound. The potassium is also going to burn with a lilac flame. What is lilac? Let's have a look at what lilac is. Lilac is a color, and lilac is basically purple, guys, okay? So we understand that sodium is going to burn slowly, going to move around slowly, and going to have a hiss sound. The same thing with lithium, slower than sodium, hiss sound. But potassium is going to move really fast, hiss sound, pop sound, lilac flame. Now, what about the interaction, the reaction between lithium and water? What kind of chemical compound do we get? Okay, let's have a look at it. So lithium reacts with water, right? Lithium, which is a metal by itself, reacting with water. So as I said before, the positive on this side reacts with the negative on this side, and the positive on this side reacts with, we don't have a negative, so we're just going to leave the hydrogen gas by itself, guys. Let's have a look here. Lithium reacting with water, okay? What do you get? Lithium will react with the negative part of the of this equation, but it's not going to be just with the oxygen. There are two hydrogens here, so lithium reacts with one of the oxygens and one of the hydrogens to get lithium hydroxide. And what do you have left? You have the hydrogen, but hydrogen by itself is always going to be H2. Okay, guys, do you understand how this works? The same thing for sodium, the same thing for potassium. So potassium reacting with water, shouldn't it just be Ko plus H2? No, guys, because this potassium reacts with the oxygen and it also reacts with one of the hydrogens. It can never, potassium, lithium and sodium, when they react with water, they cannot just form LiO or NaO or Ko. It doesn't work that way. It will react with one of the oxygens and one of the hydrogens to get either LiOH, NaOH and KOH plus hydrogen gas, and then you balance the equation, guys. You know how to balance it. So you good so far, guys? All okay? Awesome. Now we look at lithium's reaction with, we've seen the reaction of lithium with water. Now let's look at its reaction with oxygen. So straightforward experiment. You take a piece of lithium, put it on a spoon, put the spoon and the lithium in a jar that contains oxygen, and then see what happens. After that, you put some water into the gas jar, you shake it, and then you test it with red litmus paper. Let's see what happens. So lithium's reaction with oxygen. lithium is going to burn. Okay, and it burns. The colors of the flame are very important, guys. Lithium burns with a red flame, sodium burns with a yellow flame, potassium burns with a lilac flame, and lithium is going to burn the slowest, sodium in the middle, and potassium the fastest. Okay, guys, and as usual, the red litmus paper turns blue. The reason for that, we'll come to that later in acids and bases. Okay, guys, so don't worry about that. So let me just write down some of the equations for you. Lithium reacting with oxygen. This is where, when lithium reacts with oxygen, it forms lithium oxide. When it reacts with water, it forms lithium hydroxide plus the hydrogen gas. Do you see the difference, guys? All right. So lithium plus oxygen gives us Li2O, because lithium is Li plus and oxide is O2 minus. You cross multiply, you get Li2O, you balance the equation. Same thing for sodium, same thing for potassium. So, is everything okay, guys? Able to understand so far? All right. Don't worry about these equations, the lithium oxide with water and stuff. We just need to know the equations for lithium, sodium and potassium with water, and lithium, sodium and potassium with oxygen. Okay, guys, let's move on to the next part. So, okay, guys, so we've talked about lithium, sodium and potassium. What about the other elements, rubidium, cesium and francium? These work the same way as lithium, sodium and potassium. Okay, guys, they react very excessively, very strongly with both water and oxygen. So same concept. Okay, and in terms of solubility meaning the ability of the metal to dissolve in water, solubility in water. All group 1 metals are very soluble in water. Okay, unlike group 18 elements, noble gases were not soluble in water, but group 1 elements are soluble. Otherwise, they would not have formed lithium would not form LiOH plus H2, right, guys? So lithium, sodium, potassium are soluble in water. Now, we talked about safety precautions. We know these metals are super reactive. How do we prevent them from, what are the safety precautions we take? Remember, store in a particular oil that I mentioned, paraffin oil. Always store group 1 elements in group 1 metals in paraffin oil. And when you work with any group 1 elements, wear safety goggles and gloves. Safety TY goggles and gloves. Now this one is pretty logical, right, guys? Anytime they say safety precaution, just think, okay, if I want to be safe, I need to wear safety goggles and I need to wear gloves. This is always a standard answer. You can never go wrong with it. So guys, we are reaching the end of our group 1 video. We've really understood it well. The only weird thing was the melting and boiling point. I'm just going to touch that one last time. So group 1 metals, unlike group 18 noble gases, the melting and boiling point decreases as we go down the group. Why is that? Because the number of shells filled with electrons increases, so the metallic bond decreases, and so less heat is required to break the bonds. And we talked about reactivity. Reactivity is the ability to lose one electron, because all group 1 elements have one valence electron. So does reactivity increase as we go down the group? Yes, it does. Why is that? Because the distance between the nucleus and the last valence shell increases as we go down the group. When the distance increases, there's a higher tendency for that electron to be transferred, to go away. Okay, guys? The other trends are the same as group 18. Density increases as we go down, atomic radius increases as we go down. In terms of reactions with water and oxygen, just remember, guys, lithium with water, it produces hissing sound and moves slowly. Sodium moves a bit faster, produces a hissing sound. But potassium is the one with the hiss and the pop and also the lilac flame. When lithium burns in oxygen, the flame is red. When sodium burns, the flame is yellow. When potassium burns in oxygen, the flame is lilac. And to show you the equations, just using lithium plus water, okay? We don't get lithium oxide, we get lithium hydroxide. Remember this, guys, plus hydrogen gas. And for lithium's reaction with oxygen, this is where we get lithium oxide, which is Li2O. The same rule applies for sodium and potassium when it reacts to both water and oxygen. Obviously, you also have to balance the equations, guys. That was a good summary for you guys, a little repetitive, but you guys, I'm sure you're going to be able to remember this stuff. Thank you, guys. Get ready for group 17 on the next video. Cheers.